Now we can start the lecture 20 material. And the idea here is, first of all, to prove a lot of other sets are countable, but you may realise that we haven't yet proved there are any uncountable sets at all. So far, everything we've met has been countable, and we're going to meet more and more countable sets before I finally prove to you that something like the real numbers, the set of real numbers, is actually an uncountable set. So, of course, if you've already looked at my video Beyond Infinity, you'll already know why that is. Okay, so just to remind you once again, a countably infinite set has a bijection from the natural numbers to the set. But a set is countable, that means it's finite or countably infinite. So in particular, we've met a lot of countably infinite sets, and they count as countable. Okay, so the natural numbers is countable, so is Z. And in a minute we're going to see that Q, the rational numbers, is countable as well. And the set is uncountable just means it's not countable. So that makes it an infinite set which is not the same cardinality as the natural numbers. And then in terms of sequences, countably infinite you could do using a sequence where everything appears exactly once, but it's often more convenient to work with the one where you talk about a sequence that uses up the set. So this is a sequence where every element of the set A appears at least once. So in other words, this is that's where xn uses up A. And it's just unfortunate that this one only works for non-empty sets because you can't find any sequences in the empty set. Right. So let's see a few more results. That result about sequences using up sets, that was really, if you thought of a sequence as being a function from the natural numbers, that was just saying that that your non-empty set A is countable if and only if there's a surjection from the natural numbers to A. Because a surjection from the natural numbers to A is a sequence of elements of A. It's really just a sequence of elements of A where everything appears at least once. So that's, again, that's about sequences using up A. So here are some more results of this type, and I'm not going to spend too long on the details of the proof. So anything I don't prove here is an exercise, but these are, you can treat these as standard facts that you can quote unless you're asked to prove them. As usual, you're never allowed to quote a fact to prove itself. Okay, so suppose the set's countable. Suppose the set A is countable, and you manage to find a surjection from A to B, then B is countable as well. And that will follow from something we're going to do in the workshop. So I won't say more about it, but that will follow from something we're doing in the workshop that follows about composing surjections to get surjections. Because, well, there is a trivial case where they're both empty as well, but that's boring. This one about there being an injection from A into the natural numbers is quite useful. So I will say a little bit about that. Why is it that if you've got an injection from A to the natural numbers, you can find a surjection from the natural numbers onto A? I'll also say why B gives you C, because if you've got a subset of a countable set, then there's something called the inclusion map, which takes X to X, but it's from the smaller set into the bigger set, and that turned out to be an injection from the smaller set into the bigger set. So, and then you can compose two injections and get an injection, and get an injection into the natural numbers. And D is a contrapositive of C. So let's say a little bit more about some of these. So the contrapositive of D is that it's the following. If A is countable, then B is countable. So C and D are really contrapositives of each other. In disguise. So you can get from C or D to the other one. So you only need to prove one of those, and you can use B to prove C. So let's see, which one shall I say something a bit more about? So for let's assume that let's see if we can think about B. So we'll look at B. A is going to be done in workshop 10. Okay, so suppose you've got an injection from A into the natural numbers. Right, I suppose A might be, possibly A could be empty. Okay, if A is empty, that's a bit trivial. Let's say suppose. Suppose you got this one. If A is empty, then A is countable. That's a trivial special case. Otherwise, you have f of A is a subset of the natural numbers, but we don't know whether it's the whole of the natural numbers. And A is not empty. Let's take one point in A, just this is an easy way to do it. Let A naught be in A. Because we know it's not empty. And we'll choose a sequence xn contained in A as follows. Xn is equal to A naught if n is not in the image of the function. Okay? I don't care what you do with those. So if n is not in the image of this injection, which is going from A into natural numbers, just send it to A naught, don't care. I'm only interested in the other ones. Otherwise, if n is in f of A, since f is injective, there is a unique A in A with f of A equals n. It's a bit like take an inverse function, but because the thing wasn't surjective, you couldn't. But if you like, you could say the function f is sort of giving you a bijection from A to this subset of the natural numbers, and then we're going to use the inverse function on that. And that's what we're going to do here. We set xn equals A in this case. So f of xn is equal to n whenever n is in f of A. But this sequence uses up A. Well, so why? Well, a lot of the terms of the sequence may be A naught. We don't care about that. That's not particularly helpful. It gives us one of the elements of A. But everything else in A is sent to something in F of A, and which is some number n, and that n has xn equal to that element. So every element of A appears as xn for the relevant n, where f of A equals n. And that's it. For all A in A, xn is equal to A, where n equals f of A. So that's how you find out which term of the sequence gives you A. And that's it. And that's all because the function's injected. So if you've got an injection into natural numbers, then you're countable. And I think I'll leave the rest as an exercise of this result. So but some of the details you'll find in come out of some of the stuff we're going to do in the workshop. Okay. Any questions about that proof of the injection? I mean, it shouldn't come as a surprise, because you shouldn't be able to find an injection from a bigger set into a smaller set, not if it's genuinely bigger. So if it's a bigger infinity, you shouldn't be able to find an injection from it into a smaller infinity. And the same for surjections. If there's a surjection from a set onto another set, the second set shouldn't be bigger than the first one. You can't map a smaller infinite set surjectively onto a bigger infinite set, because there just isn't enough to cover it. But you have to prove these things properly sometime, and we'll see some of the details in the workshop. Right, now, this Cartesian product is quite a useful one. It's another way of getting new countable sets from old. If you take any pair of countable sets, then the Cartesian product, and I'll remind you what the Cartesian product is also a countable set. In particular, this is quite useful when you want to do n cross n or z cross n, which we're going to use in a moment. Okay? So, first recall A cross B. As we've seen many times before, it's nothing to do with multiplication. It's a set of ordered pairs, where the first coordinate is in the first set and the second coordinate is in the second set. Also, A cross B is empty if and only if at least one of the sets is empty. You only need one of them to be empty to make the Cartesian product empty, because there's no way of fitting anything in. If there's no first coordinates available, then there's nothing available. And if there's no second coordinates available, you can't find anything in there either. So you only need one of them to be empty. Okay, so the proof of the theorem. You have to get rid of the special case first. If either A or B is empty, then the Cartesian product is empty, so it's countable. A or B or both are empty, then A cross B is empty, hence countable. Otherwise, looks like we need more room. Otherwise, they're both non-empty and countable, so we can find sequences using them up. So we've got a sequence in A, using up A. And Bn in B, using up B. Now I'm going to draw an optional diagram to show you what the elements of the Cartesian product look like. So now comes an optional diagram. On the other hand, if you do the optional diagram, you don't have to give as many terms as the sequence as if you don't. The diagram helps to clarify what the sequence is that I'm going to show you. Right, so the optional diagram goes like this. I want to know what sort of things are in A cross B. Well, there are things where the first coordinate is in A and the second coordinate is B, which means that the first coordinate will be one of the A ends and the second coordinate will be one of the B ends, but probably with different indices, right? So there'll be things like A1, B2 and A5, B10 and all sorts of stuff. So let me just make a grid with some of these things in. So let's put A1, B1 there, A1, B2 there, A1, B3 there. This, you can rearrange it so your axes work however you like, okay? B3, that one. And so on, with no end of things in the first row. In the second row, we'll say A2, B2, A2, B1, and then A2, B2, and then A2, B3. This is more like matrices than Cartesian coordinates, and then that carries on. And so on. We keep I'll do one more row for you. A3, B1, A3, B2, A3, B3, and so on. And then there's no end coming down either, or down the diagonal, whatever. Goes off infinitely to the right and infinitely down, infinitely off down the diagonal. And I want to find a sequence that goes through the whole array, but it's got to be one sequence. Okay, I can see someone showing me some diagonals, which is going to be how we do it. Though actually, there are lots of different ways of doing it, as long as you've got a systematic way of doing it. Okay, so, but there are some things that you can do that are terribly wrong. You might say, okay, I'll do the first row first, and then I'll do the second row, and then I'll do the third row. But the problem is, if you do the first row first, you never get to the second row, because you've used up all the terms of your sequence on the first row. The millionth term is still in the first row. The billionth term is still in the first row. And how do you ever get to the second? The first term of the second row is the infinity plus 1th term. That doesn't make any sense, right? You've got to get to everything in the array at some finite time, though it could be a very big number, right? Same thing, you better not go down the columns, or you'll never get to the second. If you go down the first column, you'll never get to the second column. And you mustn't go down the diagonal, because you'll never get to the end of the diagonal, and you'll never get to any of the other diagonals. But you can do the finite diagonals, and that one works. So we'll do the finite diagonals. So to give you a rough idea, my proposed diagram will look something like this. These diagonals are finite. So if we first do the point at the top left, and then do the next 2 points on the next diagonal, then we've only used 3 turns of our sequence, so we're safe, we can keep going. And then another 3 turns of the sequence. So now we've done 6 turns of the sequence, and we use up the next finite diagonal. And then after 10, we've used up the next one, and 15, we use the next one. And you go through the sort of triangular numbers. If you want to figure out when do you get to a particular one of these finite diagonals, you could use the triangular numbers to figure out which ones, about how long it takes you. And you never get stuck, and you do get through all of them. So if you want to just, it's an optional diagram though, because if you give me enough turns of the sequence, I'll know you've got the right sequence. Okay? The following sequence, and there are many alternatives, but you have to give, if you just give a sequence, it's got to be very clear what your sequence is. So you've either got to give enough terms that I can see what the sequence is with no lack of clarity. And of course, if you make a mistake and you haven't done the diagram, then your sequence is going to be completely unclear and meaningless to me. Right, okay, so the following sequence uses up A cross B. So we start with A1, B1. Then I'm doing A1, B2, followed by A2, B1. So that's that one and then this one. And then I'm going to do these three. So I'll do A1, B3, A2, B2, A3, B1. And I would say that at that point the pattern becomes clear. Okay? It becomes particularly clear if you draw the diagram. If you draw the diagram, I'd probably even let you get away with giving me fewer terms of the sequence. Anyway, that's how you do the Cartesian product of two sets. And so A cross B is countable. And that is pretty much, that's one of the standard proofs. It's not the only way to do it. So I remind you that gives us, in particular, that n cross n is countable, because n is, of course, countable. And things like z cross n or z cross z and things like that are countable as well, because we already showed earlier that z is countable. So here we are proving more and more things are countable. I think in the exam last year, I asked people to go a step further and to do sort of z cross z cross z, and z cross z cross z cross z, and things like that, which you can do using this result by induction. Any questions about that proof, or where that sequence came from, or why it works? I invite you to try and figure out roughly which term in the sequence is the one which gives you A 1,000, B 2,000. So there's a little exercise for you. Approximately, you don't have to give me the exact number, which term in the sequence gives A 1,000, B 2,000. You see, that's got to be somewhere in the sequence. If it isn't, then your sequence is bad. So it must be somewhere in the sequence. If you can figure out roughly which term of the sequence that is, is it the 2 millionth term? Is it the 3,000th term? Is it the, what sort of term is it? Anyway, I'll leave that to you. So that's an exercise. I mean, of course, because the sequences could have had repeats in, I'm not really claiming there's no repeats in this sequence anyway, because they were just using up A and B, so there could have been repeats in those sequences. So this is only an approximate question in the first place. Right. So let's see what we could do with that. And I'm going to let you think about this question. Here's the function from z cross n to q. For m in z and for n in the natural numbers, it's defined, it takes, so, this mn here, this is going to be a typical element of z cross n. That means the first element should be in z and the second element should be in n. That's why m is in z and n is in the natural numbers. And I take it to m over n, which is okay, because n is a natural number and 0 is not a natural number for us, whatever it might be for somebody else. Our natural numbers are strictly positive integers, so m over n is okay. And now I want you to think, and I've zeroed the votes earlier, so you should be able to vote whatever you like, but talk about this one. Is this function an injection that's not a surjection, or is it a surjection but not an injection, or is it a bijection, or none of these, or you could ask me to explain the question again. So here you are, it's a map from z cross n to q. You might want to remind yourself of the definition of q if you haven't thought about that already. Okay, I'll pause the recording and then I'll see what votes you're going for there. Okay. Right, it would help if I turned the internet on. Okay, well, I won't bother showing you, but I'll just tell you what people have gone for. We've got 29 answers so far, and there's a fairly even split between B and C. So there's a few people going for A as well, but mostly you're evenly split between B and C. The correct answer is B. It's a surjection but not an injection. Okay, so let me first of all point out why it's not an injection. Note that f of, for example, 1, 2 is equal to f of 2, 4 is equal to a half equals 2 quarters, right? They're equal. Okay? So f is not injective. But it is surjective because of what the definition of Q is. Our definition of Q we defined it as all the m over n's you can get where m is in Z and n is a natural number. So in fact, the definition of Q, our definition, which is just the image of the function. Because that's what this set is. It's a set of all the m over n's you can get where m is in Z and n is a natural number, which means that's equal to f of m. That's all the f of m comma n's you can get where m comma n is in Z cross n. So it's surjective but not injective. But the main thing is that it's surjective, and we know that Z cross n is countable. So the corollary, we get that Q is countable. So why is that? We already know that Z and N are countable, of course. Thus, Z cross N is countable. The above gives a surjection from Z cross N onto Q. So again, reminding you that if you find a surjection between sets, the first set has to be at least as big as the second set in the informal. So you can remember which way round it is. That's the informal way of thinking about it. But more formally, we got this result earlier that we're going to prove in the workshop, that if you've got a countable set and you map it surjectively onto another set, that other set is countable as well. Okay. And another thing you can do with this approach is it's quite a nice way to prove that a countable union of countable sets is countable. That's what this result says, though, well, okay, we do it for the union of an infinite sequence of sets. Okay, that's the same as the, remember, this is the same as this thing is equal to the union over all natural numbers of AN. And you've seen some stuff about unions of infinitely many sets. So now we suppose that these A's are all countable. A1, A2, A3 is now infinitely many. We've done a union of 2. I mentioned earlier that we could do a union of 2, you could do a union of 3, but this is different. This time I need to take a union of infinitely many. But I do have to make sure that it's a countably infinite union. So the indexing set is countable here. So the natural numbers is countable, and each of the sets is countable. When I take this union, the result should still be countable. Now, this time the empty set is more of a nuisance than ever, so I'm not even going to deal with it. I'm going to say, I'm only going to give you, we're going to prove the special case when none of the sets are empty. Which is the interesting case. When none of the AN are empty. Exercise, what if some of the AN are empty? Two possibilities actually for that. One is you can throw them away and say we don't care about them because they don't affect the union. But the slightly annoying thing is that there might only be finitely many of these sets which are non-empty, and then you have to quote the finite union case to deal with it. Or you can make all the sets slightly bigger by throwing one extra element into each to make sure that none of them are empty. And then they're still countable, and then they're countable and non-empty. So you've got the choice of either ignoring the empty sets, or you can make the sets bigger to make sure that they're non-empty, but keep them countable. And either way works. But it's not very interesting. So we'll deal with the case where they're non-empty and countable. And this time I'll use the language of surjections. Then for each n in the natural numbers, there exists a surjection, which I'll call Fn, so it's a different one for each n, from the natural numbers goes to An. You could think of that as a sequence, and it would be a different sequence for each An, but I think I'll use the language of functions this time. So we've got F1 from n goes to A1 surjective, F2 goes from n to A2, all surjections. It's just unfortunate you can't do that if it's if they're empty. Okay, so and now I'm going to give you a surjection from n cross n onto the union. So I'm going to define a G from n cross n to the union from n equals 1 to infinity of An by G of Mn is equal to the nth function applied to the nth element. So if we're using the nth function, then we're going to end up in Am. And I'm taking basically the nth element in Am. But you'll get every element of every set this way. So since all of the Fn, or all of the Fm, are surjective from the natural numbers to Am, you can see that G is surjective from n cross n to the union. You get all of them. You get everything in any of the sets. The n cross n is countable, so that makes the union countable. And that's how you prove that a countable, one of the ways of proving that a countable union of countable sets is countable. So we still keep proving more and more things are countable. And we haven't yet proven that there are any uncountable sets. So it's about time we did. Okay. So we're going to finish the lecture material by proving that the open interval 0, 1 is uncountable, and I'll leave it as an exercise to you after that to prove that the other non-degenerate intervals are uncountable, because you can deduce that. In particular, the set of all real numbers is uncountable, but I'll focus on the proof for the open unit interval, and then I'll give you a break once we've proven that. We'll start the workshop a bit late, because we're overrunning, which is really because we overran the last lecture, which is really because they let us in late last lecture. So, right. Okay. So how do we prove that a set is uncountable? It's going to be using something called Cantor's diagonalization argument. So I want to prove to you that the open interval 0, 1 is an uncountable set. And we're going to do this by looking at decimal expansions. Now, some numbers have got 2 decimal expansions, like a half. We're going to stick to using infinite decimal expansions, so I'm going to want to include all the zeros at the end. So a half is 0.5000 recurring. It's also 0.4999 recurring. But the standard fact we're going to assume, just to because it's annoying, but it comes up in the proof, we need to be able to tell whether 2 real numbers are different by looking at their decimal expansions. And we have to remember that two numbers might be the same, but it can only happen if it's one of these numbers which has got 2 expansions, one ending in recurring zeros and one ending in recurring 9s. So we're going to take that as a standard fact in the proof. If you've never tried to prove that for yourself, you might want to. Make sure that there really are no other real numbers which have got 2 different decimal expansions, more than one decimal expansion. So in particular, in the middle of this proof, we're going to take a sequence of decimal digits, that's somewhere between 0, 1, 0, 1 up to 9, bn, but the bn's we're going to be using will either be 5 or 6. And then we're going to make a number out of it, which will be 0.b1, b2, b3. And once we do that, that real number has got at least one expansion made up with only 5s and 6s. So it isn't one of these numbers with more than one expansion, because they've only got expansions ending in recurring 0s and recurring 9s. So if it's made up of 5s and 6s, then it's only got one decimal expansion. And if you find another number with a decimal expansion different from that, then it's a different real number. So that's what comes up in the middle of the proof. Right, so now we're going to use Cantor's diagonal argument to prove that 0, 1 is uncountable. So we'll suppose for contradiction that the set is countable. Remember, this is a set of all real numbers between 0 and 1 inclusive. It's obviously non-empty. So our assumption tells us that there's going to be a sequence that uses up. So there's a sequence Now this is by our assumption, right? We're assuming that it's countable, and now it's non-empty. So the sequence xn in 0, 1, oops, change colour. Using up 0, 1. We assumed it's countable. It's obviously non-empty, so there's such a sequence. We need some notation. Say x1 is equal to 0.A11, A12, A13, and so on. x2 equals 0.A21, A22, A23, because we're going to need an infinite array of decimal digits. Why 0 point? Well, because it's between 0 and 1 strictly. So it does start with a 0 point. These other things are decimal digits. And generally, xn equals 0.an1, an2, an3, where the aij are decimal digits. If it's countable, you should be able to find a sequence like that which uses up all of the elements of 0, 1. But there's a problem. I'm going to show you there's a number in that sequence. What I'm going to do is I'm going to look at A11, A22, and A33. I'm going to go down the diagonal, and I'm going to choose some B's different from those. Choose a sequence Bn, either 5 or 6, as follows. Bn equals 6 if the nth diagonal term ann is 5, otherwise, Bn equals 5 if the nth term down the diagonal is not 5. So Bn is 5 or 6, and it's not equal to the nth decimal place of the nth number. Bn equals 5 or 6, and Bn is not equal to ann, which is the nth decimal place of the nth number. Now let's have a look at the number 0.B1, B2, B3. Consider B equals 0.B1, B2, B3, decimal expansion, made up of 5s or 6s. It's definitely 0.9, it's not 0.999 recurring or 0.000 recurring, so it's definitely in strictly between 0 and 1. But Bn is not equal to ann, so the nth decimal place of Bn is different from the nth decimal place of an. So Bn has nth decimal place different from the nth decimal place. Sorry, did I say Bn has nth decimal place? Bn is not right. B is the number. B has nth decimal place Bn, which is different from the nth decimal place of xn, which is ann. But B's only got one decimal expansion. So, since B has a unique decimal expansion, B is not equal to xn. But that's true for all n. So B is not in our list. It's true for all n. So B is in 0, 1, but B is not an element of that set x1, x2, x3, which was supposed to be using up 0, 1. That's a contradiction, because xn was supposed to be using up 0, 1. And that proves the result. We assumed it was countable. It was clearly not empty. We proceeded from there. We got a contradiction. Thus, 0, 1 is uncountable. Okay, sorry about going on for longer than usual, but I thought better to get it out of the way now. What we'll do is I'll give you until 10 past to, if you want to spend more time on the filling in the SEM forms using the mobile, using your mobile devices now, and then we'll start the workshop at 10 past. So it'll be a slightly shorter workshop than usual. And then next week we're just going to be doing things like talking about past exam papers, talking about the second class tests and so on.